When surface preparation fails beneath a heavy industrial coating, the result is immediate and expensive. The paint blisters, tears away from the steel, and leaves the bare metal completely exposed to corrosion. Preventing that failure comes down to one primary decision: the abrasive media you load into the blast pod. That single variable dictates your cutting speed, your labor costs, and the ultimate lifespan of the coating. For decades, sandblasting was treated as crude manual labor. You bought the cheapest sand available, pointed a hose at a rusty hull, and blasted away. But modern industrial coatings require precise surface engineering. Selecting your media based solely on the cheapest price per ton creates a false economy that almost guarantees premature coating failure. The modern baseline for heavy industrial work is the SSPC-SP 10, or NACE No. 2, near white metal standard. It requires the removal of all visible rust, mill scale, and old paint, leaving a strictly defined surface profile. It is entirely non-negotiable. This table compares the actual costs of failing to reach that standard. Using the wrong media compromises your production speed and increases your total waste volume, factors that directly inflate the project's bottom line. To balance cutting speed, surface profile, and environmental compliance, you have to weigh 6 specific selection factors. Achieving SSPC-SP 10 profitably relies on a calculation that balances upfront capital against long-term life cycle efficiency. Factor 1 is particle size. The general rule of physics here is straightforward. Your largest abrasive particle should equal the exact thickness of the coating you are trying to remove. An oversized particle stripping a thin coating creates a low hit rate, dragging down blasting speed. Factor 2, particle strength. Shoot weak media, like coal slag, and the particles violently shatter the second they impact the steel. That disintegration creates blinding clouds of environmental dust, limits operator visibility, and renders the media completely useless for recycling. Ultimately, your cutting speed and ability to recycle are dictated by the physical durability of the grain, not how much air pressure you push through the hose. Factor 3 is particle shape. The shape of the abrasive dictates the anchor pattern, or surface profile, left on the bare metal. Subangular media, like garnet, is highly aggressive. It digs in and tears away stubborn mill scale, leaving sharp, angular, microscopic peaks and valleys. Perfectly round media, like glass beads, act like tiny hammers. They create smooth dimples, providing zero mechanical grip for heavy industrial paint. This leads to factor 4, surface contamination. Sharp, brittle fragments can embed directly into the substrate, destroying coating adhesion. The physical shape of your abrasive dictates whether your coating will physically lock onto the surface or fail prematurely. Factor 5 puts those SSPC standards into practice. A true SP10 specification mandates that your media is entirely free of soluble salts, oils, and other contaminants. You also have to guard against rust rashing. If you use a coarse media that creates an anchor profile higher than your primer coat, the steel peaks will poke right through the paint and begin rusting immediately. Factor 6 covers environmental and disposal constraints, and this is where the heaviest liabilities live, especially when dealing with lead paint or contaminated field substrates. Removing hazardous coatings triggers mandatory TCLP testing. If spent media leaches heavy metals above EPA thresholds, every ounce becomes hazardous waste. Because disposal is billed by weight, mixing hazardous paint chips with tons of single-use, non-recyclable slag exponentially spikes the final project cost. Once the RCRA waste disposal fees are tallied, that cheap upfront media quickly becomes the most expensive line item on the invoice. This decision tree maps how to navigate those 6 factors by matching the media directly to your setup. Let's look at 3 environments: the blast room, the field, and the precision fabricator. If you are a high-volume industrial operator working inside enclosed, controlled blast rooms, recovery is your main advantage. Steel grit is the ultimate choice for your return on investment here. While the upfront capital for recovery equipment is high, steel grit is nearly infinitely recyclable, giving it the lowest lifecycle cost in the industry. But if you are a field and maintenance contractor working in open-air setups or temporary containment, hauling heavy steel recovery gear isn't an option. For the field, GMA garnet is optimal. It provides an aggressive, subangular pat with very low dust generation, and it can still be recycled 3 to 5 times using standard portable vacuums. Finally, if you are a precision fabricator working on delicate substrates or restorative projects, standard dry blasting will cause warping. Vapor blasting with glass beads prevents soft metal warpage by using water as a cooling lubricant. You sacrifice the heavy anchor profile needed for industrial paint, but you protect the delicate geometry of the part. The central equation of surface preparation never changes. Upfront material cost must be weighed against total project lifecycle cost. You have to stop buying abrasive simply by the ton and start buying it based on the specific surface profile you need and your true capability to recover it. Treating abrasive media as a highly engineered tool protects both your project margins and the physical asset itself.